So, I think in the last few turns we have seen the boundary conditions of Maxwell's equation. We have seen that how at a perfectly conducting surface the different electric and magnetic field would behave under different circumstances. Okay. So, we saw the Maxwell's equation, the fourth Maxwell's equation, that says that del cross B is equal to what is that? The fourth Maxwell's equation. Can any one of you tell me? Del cross B, fourth Maxwell's equation. Yeah, please. Mu naught Js plus mu naught epsilon naught del E by del T, right. So, we call this current as the surface current or a normal current. Okay. So, if you have a close look at it, you will see that this is the Ampere's law, B dot dl is equal to mu naught I. Okay. This is the Ampere's law, but how come this term came into existence? We all know that this term was added by Maxwell himself to the Ampere's law. So, what led him to add this term in the fourth Maxwell's equation? Today we will see, and this is called the displacement current. So, today we will look at the Ampere's law more critically. Okay. So, I know that Ampere's law is basically deals with current. So, what I will do, I will analyze the Ampere's law in a capacitor. This capacitor is a circular plate capacitor, two plates like this. So, I have current I going in and I coming out. Okay. This is a capacitor, this is a circular parallel plate capacitor, and I say that the radius of this plate is capital R. Okay. So, we all know that inside this capacitor there is an electric field, and which goes like this. Okay. And I know that electric field inside a capacitor E, is equal to surface charge density due to the free charges divided by k into epsilon naught. This we all know, this is basic Gauss law. Okay. You say that E dot dA is equal to rho upon epsilon naught over a closed surface. From there only we derive this. So, I can say that for this is surface charge density. Sigma free is the surface charge density due to the free charge which are causing this electric field. Okay. So, I can say here that this sigma free, if the radius is r, then sigma free is basically q upon the area of the plate. So, I can write here that this is equal to q free divided by pi capital R square into k into epsilon naught, where k is the dielectric constant of the medium inside. If we have air, k is 1. If we have something else, then it will take the dielectric constant of that particular material, dielectric material. Okay. Okay. So, now here I know that this electric field is changing. When I move from here to here, electric field is changing. Is it changing or not? Because I am moving because of the changing polarity, the electric field from here to here will be different. Okay. So, because electric field is different, so it means, and current is also, if I have a time varying current, okay, so it will induce a time varying electric field inside. because if I have a time, now the current just does not flow like this. The current goes because these plates, these circular plates are metallic. So, current will also flow on the surface of these metallic plates, and it will come like this and it will go out. So, current is also on the surface. So, it means a changing current would lead to a changing electric field inside the capacitance. But I am 100% sure that there is no current inside the capacitor because it is dielectric. Current needs a conducting medium to move through. So, I am 100% sure that there is no current inside the capacitor because the medium here is dielectric in nature. So, there is no current. Okay. So, I can say here that changing, I know that current I is equal to dq by dt. Okay. So, if current is coming from here to here and if the strength of the current is same, definitely that current is because of the free charge carrier that are available inside the capacitor. Okay. So, I can say that this is equal to dq free by dt. Okay. So, now this changing current will give rise to a changing electric field. Okay. So, I can say that dE by dt is equal to 1 upon pi r square k epsilon naught dq free by dt. Or I can say that changing electric field inside the capacitor is equal to dE by dt is equal to I divided by pi r square k epsilon naught, where we will remember that this r square is the radius of the plate of the capacitor. Okay. So, I can calculate the electric field. Now, question is, if there is an electric field, I know from Faraday that changing magnetic flux will induce an electric field. So, this changing electric field, would it induce a magnetic field? I know that here is a current. So, if a conductor is carrying a current, there is a magnetic field. In near vicinity of this conductor, there will be a magnetic field and I can calculate that magnetic field from Ampere's law. Any charge carrying conductor, any current carrying conductor will have an associated magnetic field. Okay. So, I can calculate the magnetic field here, but what about the field here inside the capacitor? Will there be a magnetic field inside the capacitor or not because of the current? Okay. So, at the first hand, I mean, what do you say? I know if suppose I have a point say P1 here, which is at a distance say small r, and then I have another point P2 at the same distance P2 at the same distance r. I have 2 points. So, what would you suggest that what would be the magnetic field at P1 and what would be the magnetic field at P2? Here current is flowing, so there should be some magnetic field that we can calculate, but what about this plane? Will there be a magnetic field or not? No, there is no magnetic field. Okay. So, you say that at P2 there is no magnetic field. So, okay, let us assume that there is no magnetic field. So, in order to calculate the magnetic field at point P1, what I will do? I will draw a closed loop around point P1, and what I will do? I will make this loop circular and I will attach an open surface to that loop. That is what my Ampere's law says. Always attach an open surface to a closed loop. So, what I will do? I will just redraw this line little inside because there is no space here. So, I will draw it here. I say this is my point P1. Now, I draw a closed loop. Okay. So, let this be my open surface area attached to this closed loop. let this be my open surface area attached to this loop, and a current I is passing through this open surface area I. So, from Ampere's law, so what will be the magnetic field at point P1? I can write from Ampere's law that at point P1 B dot dl is equal to mu naught into I. What is this I? I through the open surface. Okay. So, what is B dot d? Integral closed over a closed loop. So, what is B dot dl? B into 2 pi into small r. This radius is small r. So, what is B dot dl? The circumference of the entire circle will be B dot 2 pi r. So, I will get from here that I can write here that B is equal to mu naught I upon 2 pi r. Okay. This is not something new, we all know this, we did this in Ampere's law, we calculated, and this is perfectly fine. But now what about point P2? What about point P2? So, if I assume that there is some effect of this magnetic field at point P2, so there should be some small magnetic field. Okay, there should be some effect of the magnetic field that is existing at point P1. Okay. So, what I will do now to calculate the magnetic field at point P2, I will have to redraw an open surface. Now, that open surface need not be like this, it can be any open surface. Okay. So, what I will do now, I will draw a surface which goes like this. Now, this is my surface. So, to calculate the magnetic field, I will write down this here, dE by dt is equal to I divided by pi r square epsilon naught. I will rub this now. So, in order to calculate the field and magnetic field at point P2, at this point I will choose another surface, open surface area, and I will attach it to the same loop, because the point P1 and P2 are at the same distance. I will attach it to the open loop here. Now, you see that there is no current passing through this surface, and this open surface. Okay. Now, this is not the surface. अब आप इस surface को भूल जाइए, अब आपका surface it's like a bag, okay. So, there is no surface at the opening of the bag, there is no surface where your bag opens. So, there is no surface here. Now, the surface is the entire outer surface of the bag. So, there is no current through the outer surface of the bag, no current is passing through that surface, there is no current coming out through this surface. So, it means I can write here at point P2 B dot dl over a closed loop is equal to 0, isn't it? I can write this, and this is perfectly valid from Ampere's law. Okay. So, I say here, I conclude that B is 0 inside the capacitor, but just now I saw that a changing electrical current gives rise to a changing electric field inside. So, B cannot be 0. B cannot be 0 inside a capacitor. Is it clear? Just now I saw that there is a changing electric field inside a capacitor. When I move from this plate to this plate, electric field is changing. If there is a changing electric field, time varying electric field, then the B magnetic field inside cannot be 0. So, it means Ampere's law is inadequate. There is some problem with the Ampere's law. So, actually Faraday and Ampere both were aware of this flaw in the law. They knew that there is something wrong with the law, okay? But they could not actually foresee, or they could not at that time analyze their own findings. So, Maxwell zeroed down and he said, whether you calculate the magnetic field at point P1 or at point P2, if they are at the same distance, from the axis of the surface, central axis of the surface, the value of the magnetic field would be the same. Is it clear? Whether I calculate the field at point P2 or at point P1, if I get the field is mu 0 I upon 2 pi r at point P1, this is at P1, then because P2 is at the same distance, no matter whether it is inside the capacitor or outside the capacitor, the value of the field should be mu 0 I upon 2 pi r. Is it clear? So, this was Maxwell's conclusion. What Maxwell concluded? That value of the magnetic field at the same distance from the axis will always be the same. Okay. So, he said that if there is a changing electric field, it would lead to a changing electric flux. Okay. So, he said that I know that electric flux phi E is equal to integral E dot dA. यही होता है. E dot dA is the electric flux. So if I have a changing electric field, it will give rise to a changing electric flux. Is it clear? If my electric field is changing, my electric flux is also going to change. That is, the electric field lines coming out of unit surface area, they are also going to change because my electric field is changing. So, he said that in the Ampere's law, there should be a term here that B dot dl is equal to mu 0 I plus the changing flux should also be added. Okay. So, he added it like this. So, I will remove this and probably we also do not need this. So, he said that the Ampere law should look like this. So, the law looks like this now, that B dot dl over a closed loop is equal to mu 0 I plus k epsilon naught integral E, you can say d by dt of integral E dot dA. Now, this is what Ampere suggested. Okay. Or you can write here, let it be simple. So, you can write here that this is d phi by dt, d phi E by dt. Okay. This is, and he said that this term is the displacement current. So, now question is whether addition of this term actually helps me in clearing out the mess that is being here, that we see here. I know now that the magnetic field cannot be 0 inside, and Maxwell concludes that the value of magnetic field at P1 and P2 should be the same. So, by adding this term, which was by mere intuition at the moment, we can say that Maxwell's intuition was that the term should go like this. Of course, there was some logical reasoning behind that. So, can we now calculate the electric magnetic field inside the capacitor? So, now we will revisit the same problem again and we will try to calculate using this law. Okay. So, now let us see the point P1. Now, we want to calculate using this law. Now, this is my Ampere's law. Okay. Now, I want to calculate the magnetic field at point P1. Okay. So, at point P1 there is no changing electric field, only there is a current carrying conductor, which is, I will redraw the surface here. So, I have point R, this is point P1 and the radius, I draw a closed loop which has got a radius R, and I assume that this is my open surface. Okay. And this is the current passing through this. So, there is only current, there is no electric field. Okay. So, it means there is current, this current is there, but there is no electric field. If there is no electric field, there is no flux. So, for point P1 second term goes to 0. For point P1 second term goes to 0 because there is no electric flux associated with the surface. Clear? For this point, for point P1 the second term goes to 0 because there is no electric flux associated with this chosen open surface. So, I get B dot dl is equal to mu naught I. Okay. So, what I get? B into 2 pi r, B into 2 pi r is equal to mu 0 I, or I get the same result, mu 0 I upon 2 pi r. Is it okay? Fine? Okay. So, this is fine. Now, what about point P1, P2? So, I have point P2 here. So, what I do? I draw the same surface, I do not change anything. Now, my electric field lines are going like this. These are my electric field lines, okay. But definitely now my surface is not this surface, now it is like a bag. Now there is no current that is penetrating through the bag. There is no current that is coming out of this surface area. There is no current that is coming out at the bottom of the bag, there is no current. So, it means my first term goes to 0 at point P2. My first term is 0 at point P2 because there is no current. At point P2 there is no current coming out. So, first term goes to 0. Okay. Now, let us look at the second term. So, now let this radius be r. Okay. So, my Ampere's law now looks like this. It is mu naught epsilon naught k d phi e. So, I will write it like this, d by dt integral E dot dA. Is it okay? Now, E dot dA, you see here, this is electric field lines here. And what is the surface area, direction of the surface? Along this direction. Okay? Along this direction. So, I have here, I can write now, so E dot dA is simply magnitude of E into magnitude of dA. So, I can write here that this is equal to mu naught epsilon naught k, I will write magnitude of A into dE by dt. And this here, because this is my loop, so this is B into 2 pi r. Okay. Now, what is the area? See, here there is no electric flux. Outside the capacitor there is no flux, and here also at this point there is no flux. So, I am only interested in the flux. Flux will be generated only inside the capacitor. So, this area A is actually the area of the plate of the capacitor. Okay. Is it clear? Because there is no field outside, there is no flux outside, and there is no field here also in this region. So, the region which contains electric field is only this region. So, this area is actually pi capital R square, not small r square, okay, because r is the radius here. So, I can write that B into 2 pi small r is equal to mu naught epsilon naught k pi into capital R square. Now, dE by dt. What is dE by dt? I upon pi r square k into epsilon naught. Okay. So, I substitute this value here. So, I get I divided by pi r square k into epsilon naught. So, let us see what we get. So, I can cancel k epsilon naught, I can cancel this r, I can cancel this pi. So, what I get here is B is equal to mu naught I upon 2 pi r. So, what Maxwell predicted is actually true, isn't it? Maxwell said that at point P1 and P2, provided they are at the same distance, the value of magnetic field should be the same, and he proved that. Okay? So, it means now I have a tool to calculate the magnetic field at any given point inside a capacitor. So, now the chosen point happened to be outside the surface area of the capacitor. Although it was in between, the point, the symmetry axis was lying in between the capacitor, but the point itself was outside the capacitor. But what if I have the same point inside the capacitor, somewhere in between? So, we will try to calculate the field somewhere for a point which is inside the capacitor. Okay. So, I will redraw this drawing again. So, that is interesting. We got that the magnetic field at both the points are exactly the same. So, now I have a capacitor and the current goes like this, and let me say this is the axis, and I have my point P2 now here, and this distance I assume is small r, and this is capital R, and now I associate a small closed loop and let the open surface associated be like this. Now, I do not need a bag, okay, because it is well within the surface. So, now the electric field lines are going like this. So, for this, definitely the first term is 0. Again, for this first term is 0, there is no current, going through this surface. So, the first term is again 0. So, I will have B dot dl integral B dot dl is equal to k epsilon naught. Now, again I will have modulus of A dE by dt, right. Again the surface, the direction of area vector and electric field are parallel. So, E dot dA will again be E into A. Now, what is this A? Now, this A is actually the effective area of the plate which is in this region. I am not bothered about what is happening beyond this point. I am only bothered about the area which spans this point. So, now here this capital A is actually equal to 2 pi r square, small r square, sorry, it is equal to pi r square, where r is the small r. Okay. So, I can write here that this is equal to, I will write it down here. So, I can write that B into 2 pi r is equal to k epsilon 0 pi r square, pi small r square I divided by dE by dt will not change, pi capital R square k epsilon 0. Okay. Is it okay? The value of dE by dt will not, the R will not change. So, I can cancel out few things here. I cancel this, I cancel this, I cancel out them, and then I have 1 R goes off from here. So, what I have here is B is equal to 1 mu naught will come. So, I will have mu naught upon 2 pi capital R square into I into small r. Is it okay? So, what do you see? When I am away from the capacitor, my field falls by 1 by r. My magnetic field decreases by 1 by r. But when I move within the capacitor, my field increases by r, isn't it? So, that is amazing. So, it means I can draw a plot here. I have B here, and let this be the small r, and if this point is capital R, then I can say, if say this is B. So up to point R, the field will increase linearly because B is proportional to R. Field will increase linearly, okay? But after point R, it will fall by 1 by R. So this is proportional to R and this is proportional to 1 by R. Okay? Is it clear? So now there is a small problem that we had in our assumption. We said that field outside this region is 0, but I know that always with a capacitor there is a fringing field. At the edge there will be a fringing field. You know fringing field? You must have heard of fringing field. Whenever there is if there is electric field going like this, and if this is my surface, then I will have some field going like this. These fields are called fringing fields, and I have assumed that at this point fringing field is 0, because what I assumed that there is no flux beyond this point. There is no flux beyond this point, but actually that is not true. There is some flux here. So in reality, when you will, in principle, when you will calculate the value, maybe at this point the values might not match, okay? And the reason is because we have not considered the fringing field. We haven't considered the fringing field, okay? So this was the critical look at Ampere's law, and we all know that we have today, at least we have seen very clearly that Ampere's law was inadequate, and the correction was made by Maxwell, and from this correction he predicted that radio waves exist without anything. He did not do any experiments. Just by his theoretical modeling he could conclude, he could foresee that their radio waves do exist and they also travel at the speed of light, okay? And then there was a famous scientist called Helmholtz, you all know them. He had a very bright student called Hertz, you know him also, Hertz. He was Helmholtz's student, okay? So Helmholtz said that, can you prove Maxwell's statement, Maxwell's theoretical results, that radio waves exist, can you prove that? But Hertz said that with the existing equipment he cannot prove. So after 7 years an adequate equipment was made, and so after the 12 years of Maxwell's death, Hertz proved that radio waves do exist and they travel with the speed of light, okay? So Maxwell and Hertz, I think they were truly genius, because Maxwell, out of nothing, he could see that such things would exist, and then Hertz, after 12 or 15 years, he proved that radio waves actually existed, okay? So these contributions are actually very important contribution, because today everything, we are getting electricity only because of this law, Faraday's law, okay? So these laws are very important, because they are in a way driving our economy also. We are getting light, okay? Electricity is very important. If there is no electricity, everything will come to a standstill. There is no communication. You cannot communicate on your internet. So electricity is very important. So the people or the persons who were behind this important contribution are Maxwell and Hertz, and of course Faraday and Ampere are also there, but important contribution were made by them. And any experiments we carry out today, we see that whatever they conclude without any practical setup is 100% true. So that is the amazing thing about their theory. About 200 years from today, they could conclude all these things. So that's all for today. So if you have any doubt, you can ask. Okay.